Okay, so we'll continue on here. So let me just cover one last type of problem. I found the a better normal distribution, one that allows me to color in also. So one last type of problem, we could, just kind of change it and say, I don't know, we'll look at giraffes. How tall is a giraffe? Average height of a giraffe? Average height. What's that? It's got to be, it's like 20 feet. Okay. 16 to 20 feet, female 15. Okay, so we'll say we'll deal with a female giraffe. Okay, just because it said there was only one number. All right. So female giraffe, we'll say height follows a normal distribution with a mean of 15, and we will say standard deviation of 1.5. Okay, and I could say, what percent of female giraffes are between, we'll say 14 feet and 17 feet tall. Okay. Well, I'll just tell you how we will solve this problem. Okay. So, in the center, if we draw a normal curve, we'll have the center at 15, and basically, I'm drawing a line at 14 right here, and I'm going to draw a line at 17 right here. Okay. And the area that I'm interested in is the area in between. Okay, so I want to know what this area is. Okay, now the way we're going to get this area is by essentially I'm going to take the area to the left of 17. So let me just draw this. Okay, so I'm going to say I'm going to take this. And then, let me just shrink this down. So what I'm going to do is I'm going to take the orange area and then subtract off the blue area. Okay, so if I take the orange area and subtract off the blue area, then what I'll be left with will be the green area. Can you guys see that? Okay, it's orange on my screen. It's like brown on your screen. But so we're going to take find the area to the left of 17, and then subtract area to the left of 14. Okay. So I can express this and say, our answer. So the probability that our height 14 is that the height of y is in between 14 and 17 can also be expressed as the probability that y is less than 17 minus the probability that y is less than 14. Okay, so this is just this is expressing the exact same thing, just symbolically as well. And I just kind of want to make sure everyone's okay with this.
So you would go and find the z-score for both of them?
Yeah, you would find the z-score for both of them, find the area to the left of both of them, and then take the difference between them. But I'm just also kind of writing it symbolically here, and I just want to make sure that's okay with everybody. Okay, all right, so let's just do that. 17 minus 15 over 1.5, I get a z-score of, what, 1.33, I think? Let me just do 2 divided by 1.5. Yeah, 1.333. Okay, we would go to our z-table, look up the area to the left of 1.33. and I get 0.9082. Is that what you guys get? Alright, and I do the same thing for 14. Z is equal to 14 minus 15 over 1.5. So I think that's what, negative 0.67. And then so the area to the left, I'm just going to look it up in my table, of a negative 0.67 is 0.2514. Okay, so our picture here is this is 0.9082. This here is 0.2514. And so the area in between will be equal to 0.9082 minus 0.2514. And what is this? 0.6568. Okay, and that's what we will have here. Okay, so our answer is 65.68%, or something like that. Something around there. So far, so good? Okay. All right, in the text, there's a section on normal probability plots. You just read over it, okay? Basically, you know, there's a question of, you know, is the data I observe normal, okay? Or, you know, does the data is the data I observe normal? You know, that is, do they come from a normal distribution? Okay, and this is a tough question to answer unless you have lots of data. You know, if you just have like 100 data points, it's hard to tell, okay? I mean, and 100 data points sounds like a lot, but really, like, it's hard to know, okay? And so we have a graph called the normal probability plot, and you produce one of these. So one tool is the normal probability plot. And basically, the answer is, you know, if the normal probability plot looks like a straight line, then it's probably a normal distribution, okay? And if it doesn't look like a straight line, then it's not a normal distribution, okay? Then the data could come from a normal distribution. Yes?
Straight meaning any kind of straight, or does it have to be
You mean like right along the y? Well, the way the probability plot is constructed, if it's a straight line, it's going to look like this, okay? I don't think we need to get into the details of how the probability plot is constructed. And it's probably just useful to know that this tool exists, okay? Without needing to fully know how the thing works, I guess, you know? Like, I don't know how the inside of a calculator works, but it's still a useful tool. I can still use it, okay? Yes?
I guess question. So when you're saying if it looks like a straight line, it's probably normal.
Yeah.
And then if it's not straight, it's not normal. So if it's not straight, it's like definitely not normal. If it looks straight,
And
it's
now
certainly not
this,
perfect linear or whatever.
so yeah, so if you have a small data set, and you create a normal probability plot, it will probably look straight, okay? But if it's a small data set, it doesn't guarantee that the thing is normal either, okay?
So you have to actually know the underlying.
Yeah. I mean, this is the problem in all of statistics. It's that we are looking at just a sample of data.
Right,
and
nothing's ever going to really be a perfect.
Yeah, nothing's going to be perfect, and the question is, well, based on what I see, is the population normal? And this is actually a very difficult question to answer, okay? So one of the tools that we have is this normal probability plot. It's very useful, and you just kind of create it, and then if it looks straight, then you say, well, I guess it could be normal, okay? It doesn't say that it is normal. It's just like, normal sounds reasonable. But it's not like, oh, this is definite proof that it's normal either, okay? On the other hand, if you have a small, or you just have any data set and you create a normal probability plot and then you get like this curvature in it, then it's like, okay, I've got a pretty good suspicion that it's not normal, okay? There are more complicated tests that spit out values and say, like, this is how normal we think it is or it isn't. Even those tests, as useful as they are, they're not bulletproof and they're not foolproof. And so as far as tools go, we have the normal probability plot. Nobody would ever construct this by hand, okay? Nobody would even like try to use a computer to construct it by hand. You just kind of say, like, computer, make a normal probability plot. And then the computer will do it. And then you look at it and you go, it looks kind of straight. and I know it sounds really like, it doesn't sound like I'm selling this product very well, but it is still very useful, okay? And so, yeah, you just take the data set, you just say, computer, make the normal probability plot, and then it produces one, and then you go, it looks reasonably straight. And it's kind of, I think you just have to like look at a lot of data over time to get the sense of like what is straight enough and what is reason to believe it's not straight. And that's kind of, it's hard to fully explain that. Yeah.
Would you be able to use a regression line to see if it's straight, or is that
That is not the purpose of the normal probability plot. Okay. Yeah, you are not trying to fit any kind of regression line to it. Yeah. So, okay. So anyway, this is really just to explain that this tool exists. All right, let me, okay, I'm going to deviate from the order of the book, and I'm going to cover this topic called the normal approximation to the binomial distribution. Okay, so next week we're going to cover sampling distributions, and this is related to sampling distributions, and that's why the book kind of groups it in with chapter 5, but I also feel like it kind of breaks up the flow of the sampling distribution chapter. So I personally think it belongs more with chapter 4. The idea here is that when you have a binomial distribution and you have a large n, okay? So if you think of the binomial distribution, it's something like, I'm going to flip the coin 10 times. What's the probability the coin lands heads 6 times? Or what's the probability the coin lands heads 5 times? Or something like that, okay? And we can, we plug it into that formula that you guys learned. If I said, I'm going to flip the coin 100 times, okay, and I want to know what's the probability, and I'm no longer asking what's the probability that the coin lands heads exactly 60 times, but I ask the question, what's the probability that the coin lands heads 60 or more times, okay? You can see that this suddenly becomes a lot of work, okay, if we were to do it by hand. And what I'm explaining to you here is almost a little bit moot if you have a computer. So, but I think it also shows a neat relationship between the normal and binomial distribution. So, So, let me just kind of write this example down. Okay, so let's say, I will flip a coin 100 times. Okay, and then I'm going to ask, what is the probability that the coin lands heads 60 times or more? Okay? And so, I said for normal problems, you have to have an n, you need a p, and you need a j, right? So our n here would be 100. If we're assuming a fair coin, our p is 0.5, and our j would be what? Our j would be 60, 61, 62, all the way up to 98, 99, 100. Okay? This is like 41 calculations you'd have to do. Okay? A computer can do all 41 very quickly. But if we were to try to even ballpark this answer by hand, it would be very terrible to do. Okay? So this is where the normal approximation comes in handy. Okay? And an interesting thing is that for large n, okay, the binomial distribution looks very much like the normal distribution. Okay, and large n is defined by, large n means n times p is bigger than or equal to 10, and n times 1 minus p is bigger than or equal to 10. So if both of these check out, then we would say n is large enough. Okay? Okay. All right, and so what we can do is we can approximate our answer to the binomial question with the normal distribution. Okay. And so the normal distribution is defined by a mean and a standard deviation. Okay? And so we just need to know what mean and what standard deviation to use. Okay? And so we're going to look at the binomial distribution and say, oh, what's the mean of a binomial and what's the mean of the standard deviation of the binomial distribution. Okay? So to create a normal distribution, we need a mean and a standard deviation. Okay, so we need a mean mu and a standard deviation sigma. Okay, so recall that the binomial distribution, do you remember what the mean of a binomial distribution will be? Has mean equal to n times p and has standard deviation equal to the square root of n times p times 1 minus p. Okay? And so what we're going to do is we're going to take these and we're going to plug these into here. Okay? So we're going to just say, okay. We're going to take this and we're going to plug that into there. So our normal approximation will have mu equal to np and standard deviation equal to np 1 minus p. Okay? So for our coin flip problem, for 100 coin flips, we have normal distribution with 100 times 0.5 and standard deviation of 100 times 0.5 times 1 minus 0.5. And so this, we get a normal distribution with a mean of 50 and a standard deviation of 5. Is this okay? All right. So now our question is, so we're going to say, you know, the coin flips, so the number of heads is approximately normal with a mean of 50 and standard deviation of 5, okay? And so we can ask, so our question is now, you know, what is the probability of getting 60 or more heads? Is that so far so good? Okay. So the there is an ambiguity. Whoops. I don't want this. So I've got you know, number of heads approximately normal with mean 50 and standard deviation 5, and I want to know what is the probability of getting 60 or more heads. Okay, now there's a little bit of ambiguity. Okay, this was not a problem when we were dealing with the normal distribution. When we were dealing with the normal distribution, it was continuous, and so you know, for the normal distribution, this is like a side note. The probability, you know, if y came from a normal distribution, the probability that y was greater than or equal to, you know, I said, like, what is the probability that the height of an adult woman is over 67 inches? This is exactly equal to the probability that y is greater than 67. Okay, there's no difference between the greater than and the greater than or equal to, okay, because it's continuous. All right. When we're talking about the binomial distribution, there is a distinction. If I said, what's the probability of getting 60 or more heads, that's different from what's the probability of getting more than 60 heads. Okay? This is not the same as okay. And so we have to, there's something we do called the continuity correction, okay? And this is important because I'm going to teach you this, and I think I'm hoping you'll understand this, but what I've noticed is that in the past, students have a tendency to try to apply this continuity correction in situations where you don't need the continuity correction, okay? So I'm going to show you the continuity correction, and I'm going to say the only time you will use the continuity correction is when you are doing the normal approximation to the binomial, okay? If it's a normal problem, no continuity correction. If it's a binomial problem, no continuity correction. Only when it's the normal approximation to the binomial, do the continuity correction, okay? So do the continuity correction only when doing the normal approximation to the binomial. Okay, it's the only time you'll do it, okay? Don't do it during normal problems, don't do it during binomial problems. This is it, okay? But inevitably on the next quiz, I feel like someone's gonna mess this up. Okay, So, all right, this is what I mean by, so imagine, I'm just zooming in on part of like a normal distribution here, okay? Imagine I've got because it's binomial, it's not continuous like the normal distribution. So imagine I've got a bar centered at 60, a bar centered at 61, a bar centered, 62, so on and so forth, okay? And then I'm going to go this way to 59. Okay, and then, 58, so on and so forth. Okay, so here I want, what is the probability of getting 60 or more heads, okay? So if I were to just draw a cutoff line at 60, okay, I would miss part of this bar, okay? And so what I want to do is, if I want 60 or more heads, where should I actually draw my cutoff line? If I want to include the entire bar for 60. I don't want the bar for 59, but if I, and these bars are supposed to be centered at their, where would I draw my cutoff line? Yeah, at 59 and a half, between 59 and 60, okay? So of getting 60 or more heads, I want, I'm going to try coloring this in. I want this, okay? And so I'm going to take, so my cutoff, it will be at 59.5. Is that okay? All right, and so the fact that I'm not using 60, but I'm doing 59.5, that's the continuity correction, okay? So in all of these situations, you're either going to add a half or you're going to subtract a half, okay? And that's known as the continuity correction, okay? And so to answer my question, what's the probability of getting 60 or more heads? I would say Z is equal to 59.5 minus the mean of 50 divided by a standard deviation of 5. I get a Z-score of 1.9. And then I want the area to the right of 1.9 of Z equal to 1.9. So I can look up positive 1.9 or I can just look up negative 1.9 and I get 0.0287. Okay? And so what is the probability of getting 60 or more heads? The answer there is 2.87%. Okay, approximately. Is that okay? Yeah.
The shaded portion.
Uh-huh.
It's only going to include up to the top line of the.
So okay, so
Sorry.
all right, yeah, you
Okay.
this is what the shaded portion looks like, okay? And it's because the thing that I'm shading, I'm looking up the normal distribution here, okay? Now, the actual answer, if I did the binomial 60 plus binomial 61 plus binomial 62 all the way up, that would be the bars, okay? But you can see, like if that the green area should be very close to the bar area, right? Because like you can be like, oh, approximately this little triangle should like match up that triangle, and it should add up pretty close, and it does. It does end up very close to each other, okay? I mean, it'll be off by less than 1%.
So,
Yes.
so you're adding that 1/2 just so you get that extra little triangle.
So you're getting this half of the bar, okay? Because otherwise, I would only have
Oh, I see. Okay.
I would
Yeah.
I would not get the full bar, okay?
Okay.
Yeah. Okay. So on the other hand, if I said, what's the probability of getting more than 60 heads, where would my cutoff be there?
60.
Not at 60, but at 60.5, because I don't actually want to include the bar for 60. So the cutoff here would be 60.5. Okay, maybe so. So maybe I'll just give you another example problem that you guys can try out, and we can try this. And in the textbook, I've assigned a homework problem, and one of them will say like do it without the continuity correction. And I think when you try that problem, you'll recognize the ambiguity of trying to answer the question when it says without the continuity correction. So I almost always say like just when you're doing the normal approximation to the binomial, you should always use the continuity correction. Okay, so okay, so we'll say Steph Curry, we'll say has a 90% free throw shooting percentage. Okay, and so we will, this might not be a good assumption, but we will assume all of his shots are independent. Okay, so assume shots are independent. And maybe that's not a good assumption, but we will. All right, so we'll say we'll say over a season, or we'll say over several games. Let's say he will take, we'll say 200 free throws. Okay, what is the probability he makes at least, we'll say 175 baskets? Okay, so I'll say use a normal approximation with the continuity correction. Okay, so the key here is makes at least 175. Okay, so your first steps should be to try to say, okay, your normal model, you're going to have this mean and this standard deviation, and then solve from there. Okay, so go ahead and try that out. Where we did. Okay, so we've got a binomial distribution, right? So we've got, in this case, we're taking 200 free throws, so our n is 200, okay? And then it says a 90% free throw shooting percentage, so p will be 0.9. Okay, so our mu will be n times p at 200 times 0.9, so we get a mu of 180, and our sigma will be the square root of n times p times 1 minus p. Okay, and we're going to have 200 times 0.9 times 1 minus 0.9, or 0.1, and we get the square root of 18, and the square root of 18 is 4.243 or something like that. Okay, so I've got n is 180 and 4.243, or not n, mu. Okay, so mu is that. Okay, all right, and so we want 175 baskets or more, right? So we're just imagining a bar centered at 175. I've got a bar at 176, and then a bar at 174. So these bars should all be equal height or something. Okay. All right. Oh, and actually, because it's the curve actually goes this way. So anyway, this is the worst picture ever. Where do I want to draw my cutoff line? Because I want 175 or more. So I do want the bar for 175. I do want the bar for 176, and I do want everything this way. I don't want 174. So my cutoff is going to be at 174.5. Okay. All right, and so at this point I'm going to get a z-score. So I'm going to say z is equal to 174.5 minus the mean of 180 divided by the standard deviation of 4.2426 whatever, okay? And so when I do that, I get 174.5 minus 180. Oops, something happened. 174.5 minus 180 divided by, I'm going to just say square root of 18. Okay, that's not very helpful. And I get negative 1.296, so I'm going to round off to 1.30, okay? Is that okay? All right, and so, you know, overall, my normal distribution picture, I'm now at negative 1.3, and I want everything, the area to the right. Okay. So when I look up negative 1.3 in the table, it gives me that the area to the left is 0.0968, which means the area over here, which is what I want, right? At least 175 free throws. So I want the area to the right. This will be 1 minus 0.0968, and I get 0.9032. Okay, and so that is my answer here, okay? So the answer here is, what's the probability that he makes at least 175 baskets? 0.9032, okay? And if you want to use the shortcut, you guys said, well, the area to the right of negative 1.3 is going to be equal to the area to the left of positive 1.3. Yes, question?
So would this still be a normal distribution if it has like an upper limit of 200 and technically a lower limit of 100?
Yeah, so that's you know, okay, so this is a good objection, okay, and yes, so the normal distribution technically goes from negative infinity to positive infinity, okay? And here, obviously, Steph Curry can't make more than 200 baskets, okay? But the thing is that when you have n big, and we've defined n being big as n times p more than 10 and whatnot, is that the probability that Steph Curry is going to make all 200 out of 200 is like so close to 0 that we can kind of treat it as if anything beyond that is 0, and so we don't have to worry about it stretching off to positive infinity or negative infinity, right? So the lower end is also 0. So Steph Curry can make 0 out of 200 shots. He can also make 200 out of 200 shots. But the probability of him making all 200 free throws is incredibly small. The probability that he's going to miss all 200 free throws or even come close to that is also incredibly small. And so the actual part that looks like there has any area can be approximated with the normal distribution. Yeah. Okay. So again, this is an approximation anyway. Yeah. All right. Is this okay? Great. Okay. So I have assigned a lab this week, and so I'm going to talk about the lab here. Okay.